This page has a bunch of text on it, but before I get to it, I think it'd be easier to see an example. We're looking at singular points. You may remember we said, kind of in passing in the previous set of videos, that a point is a singular point if it zeroes out the y double prime term. Here we have x squared minus 9, the quantity squared, times y double prime, plus the quantity x plus 3y prime plus 2y is equal to 0. Since 3 and negative 3 will zero out the y double prime term, we can say that x equals 3 and negative 3 are singular points. Right now, that's just a piece of vocabulary, and you understand what it means. Singular points can be further classified as regular or irregular. For our work, we're only going to look at regular singular points in solving differential equations. We won't be dealing with any irregular singular points. In order to classify them, we put this equation into standard form. So we're going to divide x squared minus 9, the quantity squared, into all of the terms. On both sides, mind you. So for the y double prime term, all that's left is y double prime. For the term x plus 3 times y prime, we have one factor of x plus 3 that's going to divide out. And we're left with 1 over x plus 3 and then x minus 3, the quantity squared, having factored the x squared minus 9 appropriately. That's times y prime. Plus 2 over, and I'll write this one down as x plus 3, the quantity squared, times x minus 3, the quantity squared, y, is equal to 0. We can see that p of x, for what we're used to with standard form, is then equal to the function in front of y prime, so 1 over x plus 3 times x minus 3, the quantity squared. And q of x is the function that we have that's multiplied by y, so q of x here is equal to 2 over x plus 3, the quantity squared, times x minus 3, the quantity squared. Now what's about to happen is a little bit weird. First, we're going to consider the singular point x equals negative 3. We have that as a singular point because x plus 3 was a factor of the coefficient function of the y double prime term. We're going to set up an expression here, x minus that value, negative 3, times p of x. Of course, that means we have x plus 3 times p of x. Since p of x has one factor of x plus 3 in the denominator, the result is 1 over x minus 3, the quantity squared. I know, this is completely unmotivated. But based on what we've just done, we're looking at the function 1 over x minus 3, the quantity squared, and since x equals negative 3 does not zero out that denominator, we can say that the quantity of x plus 3 times p of x is analytic at x equals negative 3. And remember that that means that a power series representation centered at x equals negative 3 exists. You may be saying, wait, you said we're only going to have x equals 0. That was for solving differential equations. Right now we're analyzing singular points. Now if that felt unmotivated, so will this. We're going to take now x plus 3, that same quantity, squared, multiply it by q of x. And the result there is going to be 2 over x minus 3, the quantity squared, which is, again, analytic at x equals negative 3. That classifies x equals negative 3 as a regular singular point. We had another singular point, x equals 3. We're going to do the analogous things with x equals 3. We're going to take x minus 3 and multiply it by p of x. Notice one factor of x minus 3 is going to divide out, and we're left with 1 over x plus 3 times x minus 3. We can see that there's not a power series representation for 1 over x plus 3x minus 3 centered at x equals 3. We have an infinite discontinuity in the denominator. So x minus 3 times p of x is not analytic at x equals 3. That makes x equals 3 an irregular singular point. going back up here to our functions p of x and q of x, we can now see, we can identify a regular singular point as having, it's associated with a factor in the denominator of p of x that doesn't appear with an exponent bigger than 1, or in q of x that doesn't appear with an exponent bigger than 2. For an irregular singular point, we'll see a factor in the denominator of p of x that does appear with an exponent bigger than 1, or, we didn't see it this time, but a factor in the denominator of q of x with an exponent that's greater than 2. In your work, you'll be asked to classify singular points as regular or irregular a couple of times, but then you're going to move on to the main technique of this section here. The formal way to present what we have just been looking at is a singular point for the equation a2 of x y double prime plus a1 of x y prime plus a naught of x y equals 0 is a point x equals x naught such that a2 of x naught is equal to 0. So that's zeroing out the y double prime term. For our work, when we solve differential equations, we're only going to consider x naught equals 0. We know what standard form looks like, and since now we're just going to focus on x naught equals 0, if we multiply standard form by x squared and then relabel, lowercase p of x equals x times uppercase p of x. Lowercase q of x equals x squared times uppercase q of x. Then the standard form that got multiplied by x squared takes on a form x squared y double prime plus x lowercase p of x y prime plus q of xy is equal to 0. We'll come back to talking about this form later in this set of videos, but for right now, what I want you to notice is that this x squared y double prime plus x times thing plus other thing equals 0 kind of looks Cauchy-Euler. This is going to have nothing to do with Cauchy-Euler, but the x squared with the y double prime and the x times something with the y prime term, again, kind of resembles Cauchy-Euler. I think that anchor is going to help us later. Now, I know we've got multiple p's and q's running around. We've got analytic, regular, singular, all this stuff. I'm going to try to clarify it all right now. If we have a power series representation for both uppercase P and uppercase Q in standard form, centered around x naught equals 0 for our work, but generally speaking x naught, then P and Q are analytic at that point, and then that point is an ordinary point. If a number zeroes out the y double prime term, then we won't have a power series representation for either P and or Q centered at that point, and that point will be singular. That singular point is regular if lowercase p and lowercase q are both analytic at that point. Remember, lowercase p is x times uppercase p, and lowercase q is x squared times uppercase q. More generally, that would be x minus x naught times uppercase p and x minus x naught squared times uppercase q in the event that our point is not x equals 0. If either lowercase p or lowercase q is not analytic at x naught, then x naught is an irregular singular point. I think that's sufficient for classifying singular points as regular or irregular. You'll do that a couple of times, but then really our work is going to be with regular singular points. And now we have the main theorem for our section or this set of videos, Frobenius theorem. If x equals x naught is a regular singular point of the second order differential equation we started with here, then there's at least one solution of the form y equals x minus x naught to the r times the power series centered at x naught. The sum is at r, n goes from 0 to infinity of cn x minus x naught to the n. Multiplying that x minus x naught to the r by x minus x naught to the n results in x minus x naught to the n minus r. R is a constant that we're going to figure out as we do our work, but I want you to think of r as an integer or a fraction, just some number. And because in our work x naught is going to equal 0, our starting point is going to be y equals the sum as n goes from 0 to infinity of c sub n x to the n plus r. That's really the takeaway. If we either have an xy double prime in our differential equation or an x squared y double prime, then our proposed form of solution is going to be a power series that has, instead of x to the n, x to the n plus r. We'll explore the implications of this in the next video.